Welcome all. Today, this video is about walk around of the project Wall Robo. It's a simple area coverage algorithm implementation. Okay, so let's first discuss the problem statement. Then I will show you the demo, how this is gonna work. Okay, and then we will see the code base. Okay, so the problem states that we have a wall. Okay, and user will give the dimensions of the wall. Let's say height and width, and user will also input the number of obstacles and their positions with their respective dimensions. So let's say I will have the left bottom point of two obstacles here. So let's say it's x1 y1 and it's x2 y2 with some width w1 and let's say height h1, and here it's w2 and h2 for the obstacle 2. Okay, now our aim is to color the remaining area here, remaining area of the wall. So this is the problem. Okay, so I want you to first see the demo, then we will discuss the solution and the code base review. So in the top left corner, you can see that we have the place to fill the width and the height of the wall. Okay, and then we can add obstacles as much as we want. So let's add two obstacles and let's provide their position and width and height. Okay, then we will click the add wall or submit wall, and we will have the complete wall map with respective segments. And when we click the create trajectory, it will generate the separate trajectory paths for each segment. Okay, and then if I click the play button, it will start painting each segment. Okay, segment wise, and I can also control the animation speed here just to observe the robo carefully. Okay, how it's behaving. So yeah, that's it. Let's see it once again. I can replay this also. Now let's discuss about the solution. How we're gonna solve this problem. So I came up with a simple approach. So what we're gonna do is, suppose if we have a empty space with no obstacles, then the best way is to traverse in a zigzag way, snake-like order, like this. Similar pattern we're gonna apply here, but with a little bit of optimization. What I thought was is that no need to go over the obstacles. So what we can do is we can divide this into several sections like this. And this is section 1, this is section 2, and this is section 3 here, and this is section 4, this is section 5, 6, and 7. And for separately for each section, we can have the same trajectory. Like in this section, I can go like this, right? For some other section, I can go similarly like this. At present, there is like we are moving from one section to other section in a sequence, but what I thought was to implement is that we will have different sections and we will compute some kind of like minimum spanning tree or something, like, so that we have to traverse between the sections in a best suitable way. But unfortunately it's not I am not able to implement this. So at present the switching between the sections is in a sequence. It's not optimized, so it's one after another, and we'll traverse in each section in the similar way, in the zigzag way, and we have a trajectory of the robo for each section separately. Okay, so now let's discuss the DB schema, how we're going to implement the DB schema. So for a wall, what all things I have ID, right, primary key, and then I will have width of the wall and height of the wall, right? That's it. And for each wall I can have obstacles, right? I can have many obstacles for each wall. So I will have another obstacle table here, and in obstacles I will again have the ID of the obstacles. And because many obstacles can have a single wall, right? So I will add wall ID also here as a foreign key. Okay, and then every obstacle can have their position x and y, and what else, width and height. Okay, similarly, what else we have to store? So see, after calculating the segments, so let's say this is our wall in which, let's say, we have an object here. So suppose we have a segment here. Okay, this segment, we want to store this segment. So how can we store this segment? So if you look carefully, we can store it similar to the obstacles. We can have the left bottom part. Okay, we can just store the left bottom part xy as the position and the width and the height of the segment. Okay, width and the height of the segment, and rest will be very similar to the obstacle. So wall can have many segments also, right? So we will have another table for segments. This will also have the ID as primary key and wall ID as foreign key. Okay, and there is one more thing. Every segment will have its own trajectories, right? Every segment will have its own trajectory. Trajectory in the sense I'm saying that in trajectory we are storing nothing but the sequence of points, like from which point to which point the robo will move. Okay, so how I'm storing this? So we will have again one-to-many connection here. So a segment will have segment trajectory, let's say, and what this will have ID and section ID, segment ID or section ID, whatever you can say, section ID or segment ID as foreign key. Okay, and then we will have sequence and X and Y. Why I'm saying this? For every XY point which I'm storing here, I should store its sequence also, like say this is at sequence 1, this is at sequence 2, this is at sequence 3, this is at sequence 4. Okay, so I will store also the sequence. So that's it. That's the DB schema as a whole. And one more thing, because we need to log the responses also, I mean request responses also. So we'll have a separate table for logging. In this, let's name it API logs, and we will have ID, endpoint name, and method, which method getting called, request time, how much time it's taking to fulfill that request. Okay, that's it. So let's look it into a more clear fashion in the repo. Okay, so here is our code base. Yeah, so in the readme, yeah, see the diagram, we have the walls. Every wall can have many obstacles and many wall sections, and every wall section can have many section trajectory. Okay, so and we have a separate table for the logging responses, request responses. So yeah, so in the databases, discuss few things. So in initDB, we have our initialization of the database using SQLite. Yeah, so here you will see we will have walls table, then we have created the obstacle table. Okay, and if you look carefully, we have cursor.execute create index if not exist idx obstacles wall on obstacles wall ID. This is just to make the query faster. You know, whenever we want to query, like for a certain wall ID, I want to get the all the obstacles. So it's for the internal use only. It's not stored in any table or anything. Just to make the query faster in SQLite. Similarly, we will have different other indices also in the file. And we have connection.py to get the connection from the DB. Okay. Then we have crud.py to do the CRUD operations, but we will see them later when we discuss the rest of the code base. So let's start. So let's start from the main.py file first. Yeah. So in the main.py file, you will see first we have a middleware, app.middleware to log requests. Okay. So if you go here, if you see here in the middlewares, we have logging.py file. Here, what we're doing is we are before calling calling HTTP request, we are initializing start time, and after the request, we are getting process time as current time minus the start time. Okay, and then we are getting the connection, and then we are simply storing the request in the API log table. Okay, and then we are committing the changes, closing the connection, and returning the response. So that's it for the logging part. Now again, let's go to the main.py file. Here, next thing is serving static frontend. Yeah, so our frontend is static. We are serving it at this endpoint at /static. Okay, and then initializing database. initDB is just running this initdb.py file, which we have just saw earlier, to initialize the database. And then we have two routes. Two routers here, app.include router, walls.router, and trajectory.router. Let's see what walls.router has. So in the app folder, if we go into the routers here, you will see we have two routers. Let's first see the walls router, walls.py. Yeah. So in this, we have two routes, one post route to add wall and one get route to get the latest wall details. So let's see what this add wall post route will do. So in this, this function is taking data as a type wall input. So from where this wall input type is coming is, we have defined somewhere this, see in the app.py file, we have models.py. Okay, just the type for a little bit type checking. So for obstacles, we have XY, the position and width and height, all are integer type. And wall input, for wall input, we have width, height, and obstacles. For simplicity, I have taken all of them as integers. Okay, and obstacles will have list of obstacles type. Now again to the walls.py file. So in this, we will get the data as wall input type. Okay, and then we are calling a function create grid. Okay, and it is returning as a grid. It is taking width, height, and all the obstacles. Okay, so let's see this create grid function where this is. So this is in planner.py file. So let's go to the planner.py file and see. So the create grid function, what this is doing is, let's see here. This create grid function is making a grid, marking everything as 1 initially, 1, 1, 1, 1, 1, 1, and whenever we have an obstacle, it will marking it as 0. That's it. That's how the create grid function is working. Now again, back to the walls.py here. So our grid is getting generated. Now we are again calling find free rectangles. This function, what this is doing is it is actually calculating the sections and returning sections. So let's see how this is working. Find free rectangle. It is again in the planner.py file here. Yeah, find free rectangles. So we are starting from the left top corner and we are traversing in this way. Okay, so whenever we reach an end or we reach an obstacle, suppose if we have an obstacle here, okay, then we will stop here. This will be our like maximum width. Okay, from here we are getting our maximum width, and then in the next iteration, what we will do, we will again start from here. Okay, we will see if it is not in any obstacle or something, this cell, again we will go like this and we will go till the maximum width if it is possible. Okay, and next time, let's say this obstacle came here, so we got an obstacle before maximum width, so we will not count this height, and we will count the maximum height till this point. So like this we will get maximum height. Okay, so let's see in the code again. So if you see, we are getting the maximum width. Okay, we have defined the rectangle initialized with x, y, 0, 0. This is the initial position of the section, and width and height of the section initialized with 0. And for finding the maximum width, we are doing the similar thing. If x, the initial position, plus the width of the rectangle is less than wall, and it should be less than the width of the wall, and the value at this position should be 1, that there is no obstacle and it is not visited. Okay, then we will increase the width. If we reach the end of the wall, or we get an obstacle, or if it is already visited, then we will not increase the width, and this will be the maximum width of the section. Okay, and in the height, again we are doing very similar things as we discussed. Y plus the height of the section should be less than the height of the wall, and for all, okay, here see, for all grid, the value should be 1. For all the cells, the grid value should be 1, that there should be no obstacle, it should not be visited. Okay, for all the W in ranges, this is this. So so when we get an obstacle here, okay, prematurely we will get an obstacle here. So here the cell value is not 1, okay, and it should be 1 for all the cells. Then only we will increase the height. So here in this position, in this case, because the cell value is not 1, so we will not increase the height in that case. Okay, and then we will mark all the cells visited in this segment range, and we will append the rectangles dimension, the segment dimension, into the rectangles, and we will return the rectangles, which is a list of dictionary. Okay, and the dictionary will have the positions and the dimensions for each segment. Now what else? Let's again go to the walls.py. So we have calculated the grid, okay, created the grid, calculated the sections. Now wall id equals to current.insert wall. What this is doing is, this function is inserting the wall with the obstacles into the DB, okay, with sections measurement, which we have calculated previously. So if you see in database, we have a crud.py file. In crud.py file, we will have this. Yeah. So in this, see, we have an insert wall function. It will take height, width, and obstacles as a list of dictionary, okay, and sections also. And I'm just getting the connection, running a simple query for all the obstacles, OB into the obstacles, and all for sec in the sections, and I'm inserting every obstacle into the obstacle table and every section into the sections table, okay, and height and width of the wall into the wall table. So yeah, I think that's all for the walls.py route. Let's check once again. Yeah, and at the end, if everything went fine, we will return the wall edit successfully. Now the second endpoint is latest wall. It's a get route, okay. So what this is doing is, it is just performing a simple query to get the latest wall. Let's see this. This is also into the crud.py file. The function is defined in crud.py file. Let's see this. So yeah, in get latest, if you see, I'm getting the connection, and from walls, see cursor.execute, select star from walls, order by in descending order, limit 1. So in descending order from walls, the topmost row will be the latest wall ID and the dimensions of the latest wall. Okay, so I will get that. Okay, I'm doing this wall equals to cursor dot fetch one, and then first I will get the wall ID, width and height of the wall. Then I will again execute a query to get the height, width and position of obstacles. Similarly for the sections, all the segments. Okay, and then at the end what I will return? I will return the wall ID, wall width, wall height, obstacles and sections. Okay, so that's it, I think. And yeah, and at the end we will return wall here. This wall will have all the wall height, width, position of the obstacles, their dimensions, and segments and their dimensions. Now we have in the main file, if you see again in the main file, we'll have another router here, trajectory.router. So let's see this trajectory file in the router folder. So here we have two routes here. One is to we have only one route here to calculate the trajectory. And for calculating the trajectory, it is taking input wall ID. Brush size here is the paint robo size, which I put constant, but in future of course it can be changed. And what it's doing is it is calculating trajectory for each segment. Okay, and yeah, and saving this. So let's see what all the functions it's doing. So first we are getting the wall, wall equals to current.get latest wall. Okay, so it will fetch the wall, and then it will get the sections from the wall, this wall rectangles. Okay, because rectangles is storing the all the sections. Okay, then to store the trajectory we will have a empty array, let's say section path, and then we are processing this section wise. Okay, segment wise. So for each segment in sections, this means this sec will have the segment bottom left positions and the width and height. Okay, so first we will create a grid, okay, for the segment. Then we will compute the zigzag path, and we will adjust the coordinates to the wall coordinates. What this is saying is, okay, yeah. So see here. So let me explain you what this is doing here is. Let's say we have in our wall, we have this segment. Okay, this is our segment. Now, first what we are doing is we are getting the dimensions of the segment. Okay, and relatively we are calculating the path trajectories here, the points. Okay, so any point here, let's say which is at a comma b, in the real wall it is at a distance. If I say it's x comma y, it is at a distance this point will be a distance x plus a comma y plus b, right? So this is what happening here is, if you see in the code, this zigzag path is calculated first on the dimensions of the grid. Okay, grid which is of size of the segment. Then in adjusted path we are just adding these xy to the all the points in the path, all the xy points in the path. Okay, then we are saving the trajectory path for the segment, okay, using a CRUD operation into the DB, and in our segment, in a section path object, we are appending it in a dictionary format for every segment ID. Like for every segment in a wall, we are storing the adjusted path, this adjusted path which is a list of the tuples xy. Okay, so that's it. And then we are calculating what these are some few metrics, like calculating the total number of cells, and then I took an assumption to calculate the total time. It's like per unit time a row is covering 2 cells, so it's just total time is total cells by 2, and at the end we are returning total cells traversed, total time units, and section path. So I think that's it for the trajectory.py file. Now in planner.py I think we have covered all the functions. Yeah, I think we have basically covered all the project in a brief. So at the end, I just want to tell how to run the project. First, we need to create the virtual environment, and then install the dependencies from requirements.txt, and simply we can run the app from here. Okay, and then we can see the web-based UI here at this link. Okay, so yeah, that's all. Let's see a demo again with some different values of the obstacle and wall. Okay, so let's see the demo again with more obstacles. Okay, I know there are a lot of edge cases in the project right now regarding the position, the units, and also because I took everything as integer to simplify the equation, the brush size and the paint thickness and everything. There are a lot of n number of optimizations which can be done, but I hope till now this project makes some sense, and that's all from my side. Thank you.